Morning class. Okay, so I'm pre-recording this lecture because my kids have a regular old-fashioned snow day, so they're all home. So just hoping to get it pre-recorded so there are fewer interruptions from upstairs where they're all at. This will allow you to pause and kind of catch up on notes as you go. So I've got the guided notes right in front of me. So hopefully I don't miss anything and kind of move through them smoothly. So this isn't going to be a super long lecture. I just want to move ahead enough so that we are ready to do some more hands-on lab activities, hopefully tomorrow when I see you in in-person class. So first of all, open up for me, and then you can pause the lecture while you're opening it. Open up the lecture 2, unit 2, lecture 2 guided notes. And then we're also going to be moving into unit 2, lecture 3 guided notes. I'll give you a pause when you're switching between the 2, sorry. So open up the unit 2, lecture 2 guided notes, and we went through almost all of that. So that's where we were talking about the physical and chemical properties. We spent a lot of time on density. We looked at chemical properties, we looked at physical and chemical changes, and some of the signs that those changes might occur. Those are things we're going to be looking at tomorrow in an in-person lab. We're going to do our first chemical reactions lab, which is hopefully exciting. Um, so we'll get to get a better look at, remember I mentioned like a precipitate and what does that look like? Color change I think is pretty obvious. Release of a gas, pretty obvious. But some of those things we talked about last week in class. Okay, so if you scroll all the way to the bottom of those notes, the one thing that we did not get to is the law of conservation of mass, or some people will call this the law of conservation of matter. Now, I believe this is, again, something you've heard before, but I want to make sure that we all have this down in our notes because it is super important stuff. So the law of conservation of mass, or the law of conservation of matter, states that mass cannot be created nor destroyed, which really means mass matter cannot be created nor destroyed. So in any of these changes that we're talking about, whether it's a chemical change or a physical change, an extremely high energy reaction or something really slow and simple like a leaf changing color in the fall, these things still conserve mass or matter. So matter may go from one form to another, from one place to another, but you cannot create it or destroy it. So in essence, it says that all the matter that's in the known universe today, if we take this big scale, so all the matter that's in the known universe today was there present at its beginning. So it's certainly changed form. In astronomy, we've looked at like the galaxies and stars and things that this matter has become, but it is the same amount that was there in the beginning. So that is that law. Now, Einstein kind of changes it up slightly, and I'd like to talk to you about that in astronomy on Friday. So I'm actually going to kind of go back on some of those words that I just said. But for now, we'll just say law of conservation or mass or matter. Okay, so now pause and open up your Unit 2, Lecture 3 guided notes if you do not have those in front of you. And when you have them ready, unpause me and I will go through some of that. Okay, so part 3 of the unit has us really focusing on the states of matter, temperature, what it is, behavior of particles, and how that all kind of links together. Okay, so we're not going to do all those guided notes right now. I'm just going to get you through some of the beginnings of it. And then if there's questions on this, I am happy to answer them at any time, but definitely when I see you in class next, we can kind of talk about anything here that's not clear. I'm not really going to use the board behind me because there's no math in these notes. So I'm just going to kind of talk, and again, if you miss something, you can just pause me and kind of rewind, and hopefully you'll get everything down in your notes. Okay, so the first thing you see at the top of those notes is energy review. So I'm sure that you've heard the word energy before in a science course. We're going to be looking at a couple of different types of energy. There are many, many types of energies and sources of energy. So we're going to just talk about a couple of those. And so the first one is thermal energy. So that's that first blank on your guided notes, thermal energy. And so thermal energy is the total kinetic and potential energy of particles in an object. So we can call that its thermal energy. Again, the physics teacher in me I'm simplifying it a little bit, so it's kind of bugging me. But for now, we'll call that the thermal energy. So thermal energy of an object depends on two things, and these are not those next two blanks. Okay, I didn't put this in your notes, but it depends on two different things. So if I'm talking about total thermal energy of an object, it depends on the temperature of the substance itself. So the higher the temperature, the more thermal energy something will have. And it depends on the number of particles in the sample. Okay, so if I have two things that are 100 degrees Fahrenheit, so that's like warm water. So for instance, on the slide, if we were in class, I had a picture of a hot tub and a cup of water. So a hot tub contains many gallons of water. A cup of water is just a cup, right? So if both of those samples of water had the same temperature, then they still have different thermal energies. The hot tub would have a lot more total thermal energy just because there's so much more water in it. So if I'm adding up all the kinetic energies and potential energies of the water molecules, there's more available in the larger substance. So it depends on the temperature of the substance. So warmer things have more thermal energy than cooler things, but it also depends on the number of particles in the actual sample. So that's thermal energy. Now, I mentioned two different types of energy with thermal energy. Those were kinetic and potential. Again, I'm going to guess you've heard those words before. Maybe you did like roller coaster problems or things like that in junior high. But this is also really important when we're talking about small things like particles. So, kinetic energy is the energy of things in motion. Anytime something is moving, it has some kinetic energy. And there's equations you can use to calculate that. Potential energy we called stored energy. It means something has the potential to move. And there's several different types of potential energy, several different ways you can have the potential to move. For instance, you probably talked about if something's held up high, then it has a great potential to fall, right? That's gravitational potential energy. I could take here, I have a ponytail. Right now, it really doesn't have potential energy. As soon as I stretch it, right, it has the potential to move. I gave it something called elastic potential energy. There's electrical potential energies. There's all kinds of different potential energies. Okay, so potential energy is stored energy. Kinetic energy is energy of motion. And so how these energies work tells us about how particles move and kind of tells us what temperature is and even can be used to explore states of matter. So that's the idea. Okay, so kinetic molecular theory or the kinetic theory of matter. It's kind of both terms used interchangeably. Sorry, it's really early. Coffee pause. Okay, kinetic molecular theory. I'm kind of, again, making sure I follow along your guided notes. Kinetic molecular theory says that all matter is made of small particles, very small particles. You can imagine, this isn't exactly what they are, but you can imagine them as being tiny, tiny little balls or spheres if you want to have a visual in your head. Those particles are in constant random motion. So we know that all matter is made up of particles. The particles are in constant random motion. And there's a third part of the kinetic theory of matter. And the third part of matter, or the kinetic theory of matter, says that the motion causes the particles to collide with each other and with the sides of whatever container that they are in. Okay, so those three things, it doesn't really seem that significant, but they truly are, and we'll talk about that more over the course of the next week. So those are the 3 points of the kinetic theory of matter. All matter made of tiny or small particles. Those particles are in constant random motion, and that random motion causes those particles to collide with each other and with the walls of any container that they are in. Okay, so then I had in their guided notes a section of observations of, excuse me, particles in motion. So what we notice is the higher the temperature, the faster the particles. Okay, I'll repeat that. That's thing number one that we observe with particles in motion. The higher the temperature, the faster the particles, the faster they'll move. So that's observation number one. Observation number two, at the same temperature, massive particles move more slowly than the smaller ones. That kind of makes sense if you think about that, right? That's pretty typical. So if you have particles at the same temperature, the massive ones move more slowly than the lighter ones. And then observation number three is that this kinetic theory of matter will explain the differences between the states of matter. So we're going to use this kinetic theory of matter to explain the differences between the states of matter, meaning we'll focus on solid, liquid, gas, because that's what you use most on Earth. Okay, so those are our 3 observations. So for kinetic theory of matter, you have the 3 points of the actual theory, and you need to know those. And then using that theory and an experiment, really, we have those 3 observations regarding motion of matter. Okay, all right. So we're going to jump into temperature and do a quick review of solids, liquids, and gases, and that will be the end of today's short lecture. Okay, temperature. Temperature is not a bad definition, would be how hot or cold an object is. We don't like to use the words hot or cold in our definition of temperature. So temperature is actually, the scientific definition is that it is the measure of the average kinetic energy of the particles in a substance. The measure of the average kinetic energy of the particles in a substance. Now we say average because all of the particles in the substance are moving at slightly different velocities. So I'm using this may just seem more confusing. So if this doesn't make sense, that's okay. And I see I have some bad glare. Oh, you can't really see it very well. But if we were going to plot the so this is like the number of molecules. So let's say I have like a sample of water or something. And so there's really billions of molecules in it. Again, I know you can't see that really well. I'm sorry. I see my markers down. And this is the velocity. That looks a little bit better. Okay, so I have the velocity, and this is the number of particles on the bottom. If I were going to kind of plot, it's not like all of the particles have the same velocity. Okay, so if I have a sample of matter like water, this is a bad graph, it's not true. Not every molecule in there, they're all moving just a little bit. Remember, we just said that's a kinetic theory of matter. Water is made of tiny particles. Particles are in constant random motion. They do not all move the same way. What we see time and time again are these kind of curves. Okay, so hopefully you can see that shape. That's all that matters. Again, I see a big glare. I apologize. So you see you have this kind of curve. So in a sample of any matter, whether it's solid, liquid, gas, a molecule, an element, you will have this kind of curve that would describe its motion, which means some of the particles are moving really, really slowly down at this low velocity. Some of the particles are moving really, really quickly, and there's a lot so you have to find the average, right? So you can kind of graph that out. I mean, we're not going to, but that's what you would do in higher level chemistry. So when we say temperature is the measure of the average kinetic energy of an object, that's kind of what we're saying. Okay, so the higher the temperature, the higher the average kinetic energy, which means the higher the temperature, the faster the particles are moving. So if you think about those states of matter, because when I say solid, liquid, gas, I think you have a sense of the properties of all 3 of those already. When I talk about those states of matter, as you can imagine, a solid is a state of matter where there's not much room for motion. You have these tiny little vibrations occurring. So typically, if you take a substance, it's going to be in a solid state at lower temperatures, and then something like the gaseous state where it can move a whole lot more freely at higher temperatures because it needs more kinetic energy to move like that. Okay, so let's review the states of matter. So again, today when you're not with me in person, we're just going to do solid, liquid, gas because I know you've seen those on repeat. Tomorrow when I see you in person, there's actually 2 more. I've been saying 1 more, but there's plasma, and then there's something called the Bose-Einstein condensate, and it's like pretty cool stuff, and probably some technology that will impact our life. So anyways, we'll kind of explore that as well. Okay, so solids. Let's look at solids. So properties of solids. We know that solids have fixed volumes and fixed shapes, right? Solids have fixed volumes and fixed shapes. The particles are held tightly together in a rigid structure. The particles have a low average kinetic energy compared to the other states. Because of this, the particle motion is limited just to vibration, right? They can't move freely because they're in this rigid structure. There are 2 types of solids. Those 2 types of solids are crystalline and amorphous. Let me again write it on the board. Let's see, can you see down here? I'm just going to spell it for you. Crystalline and amorphous. We'll get into that a little bit more. I'm hoping in a lab next week, so you can kind of see the two. Crystalline is something with a very patterned structure. So, for instance, table salt, and any sample of table salt would have the same structure on the microscopic level. So I expect it to look the same all the time. Something that's amorphous is not that way. It also can sort of flex and change its shape, but it's still not a liquid. So something like Play-Doh, chewing gum, cotton candy. These are things that have a more amorphous structure. Okay, so crystalline is that set. I mean, they're all rigid shapes, but set, very rigid structure. Looks like a crystal. That's where the name comes in. And amorphous does not. So that's a solid. Liquids. Properties of liquids. Liquids have that fixed volume, but their shape changes depending on the container that they are in. The particles have more kinetic energy than solids, and particles can flow or slide past each other. Particles can flow or slide past each other. So a liquid is a type of fluid. Anything that you can pour is a fluid. So liquid and gas is also a fluid as well. All right, so that's liquid. And then gases. Gases do not have a fixed shape or volume. So if confined, the gas particles will spread out to fill their container. Gas particles always spread out to fill whatever container they are in. So you can take them and compress them into a really small space, or you can allow them to fill a space like a room. This process of the gas filling the space it's in is called diffusion. Diffusion is the process in which a gas fills the space that it is given. Of those states of matter that we're talking about, gases have the highest average kinetic energy. The energy is high enough to overcome any forces that hold the particles together, not the molecules, okay? So they're not overcoming bonds, but they are breaking those particles apart so they can all move freely and individually. And so in a gas, we would say that the particles can freely move. Gases of the three states of matter, that's what we've got most prevalent on Earth, not in the universe, but on Earth. And there's a lot of properties that go with gases, kind of, so we'll get into that later, but exploring what happens if we change, because we can manipulate them pretty well since they're not in a rigid structure. So what happens if we change the volume that they're in? What would happen, for instance, to the temperature? What would happen to the pressure? So those are things that we'll really spend some time exploring in about a week and a half. Okay, so that is where I'm going to stop. Now, the lab activity that you have for the rest of the bell so if you want to start it before you check in at the end of the bell on Google Meet, there is a lab activity that has you exploring the conservation of mass or matter that we discussed. So I encourage you to use snow, but you can try something else as well. Ice would work as well. So you're going to take that snow or ice through a physical change, which is melting. And so using your lab box materials, namely you have a scale in there, right? And you could use something else, like if you want to put the snow in like a Ziploc bag or something, a cup. But you are going to prove that law of conservation of mass. So it's really simple in terms of procedure. There's multiple ways to do it, so I'm going to let you figure it out. Essentially, you need to know the mass before it melts, the mass after it melts, and keep it as an isolated system. So that assignment asks you to write up your procedure, which is probably just a couple of steps, but you also need to take a picture. So use your cell phone, or you can even use your computer to take a picture of whatever your setup is and attach it to that document. So when you submit it before class tomorrow, you're going to have your mass before and after the change, which hopefully are about the same. You're going to have a picture of what you did and just like real quick steps of what you did. So if you want to go start that right now, you can, and you should be checking back in so we can see if you have any questions or just to go over things at about 11:10.